That mic's on now.
Cool, and then we'll open the camera, and then cool, and then you can stop the.
I'm turning the mic on.
And then you can go back to the audio and turn it off.
Yeah, if anyone wants to help with grabbing it, I usually do it.
Cool, ready?
Yeah. Excellent. So at least know enough to get confused.
Hi everyone, welcome to Future Faces of Physics 2021. We are the Colorado School of Mines Society of Physics Students. It is a club on campus where we basically reach out to different schools, talk about physics. Also, we create a community between one another so we can engage in social events as well as benefit our own academics through physics and STEM in general. So we hope that you really enjoyed this session. We're going to show you a lot of demos and also have a Q&A at the end where you can ask current college students about their experiences in college. So I am Austin Holmes, and I'm the VP of Outreach for Society of Physics students. And good luck. Hope you guys enjoy.
Hello and good morning, everyone. I am the current president of SPS, and I want to thank all of you for showing up today. My name is Joshua Lewis, and I hope you learn a lot about some very interesting physics. Yes.
Right. Hello, my name is Ashley Howard. I'm the VP of Communications here for SPS, and I am super excited to get to show everybody some really awesome things.
Hello, I am Alex Mikulich. I'm VP of InReach at SPS, and like what they said, I think physics is super interesting, and we have a whole bunch of different demos to show you in basically all different realms of physics, which does include pretty much everything in life, like optics, sound, gravity, electricity. So yeah, hope you guys learned something, and if you guys don't, then go ahead and ask questions. We'd be happy to answer.
Hello, my name is Paul Brosey. I'm a sophomore in the SPS club. I'm just a regular member. And here at Mines, I do a lot of research. One of the things with like quantum computing. So there's a lot of really interesting things. A lot of the people here are doing pretty interesting research and want to talk about how much they enjoy physics. So I hope you learn a lot today and enjoy it a lot.
Picture quality is really good. Excellent. Can we start with the demos?
Hello, my name's Ami Lam. I am a freshman at Mines, and I don't have a lot of experience in the more upper level courses, but I can give you insight on what it's like to be a first year learning STEM and a lot of the general courses. So I hope you have a lot of fun on this live stream today. Thank you.
Alright, well, today we're going to start off by showing you the pizza problem. So basically what this is, so if you think about it, there's many different ways for a weight like this to get from the top of the hill to the bottom of the hill, but which way is the fastest? Now, it might seem intuitive that the fastest way to get down there is also the shortest way. So if you look right here, there's two ramps. One of them is flat like this, and then the other one is curved. But, you know, which one is actually going to be fastest? Well, we can actually see this by doing a race. If you want to see, so these are two equally weighted objects, although the weight of the objects doesn't actually matter because they'll still fall at the same rate. But let's go ahead and see which one actually makes it to the bottom first. Ready? So yeah, there was no contest. Clearly this pizza corn right here went a lot faster. Now the word for pizza corn just means the fastest way to get from the big object, the higher object up here, to the bottom level down there. Now, it turns out that this shape right here is actually called a
One.
Alright, sorry about that. So back to this topic. A Cartesian probe is the shape that you get when you try to find the fastest way between an object or for an object at a higher level to get to a lower level. Now it turns out that the shape of this Cartesian probe is called a cycloid. Now that's the shape that you get if you put a pencil on a wheel and you roll the wheel across the surface, you get kind of this elongated curve. And it turns out that is the fastest way for an object like this to get to the bottom. Now, this is because initially the acceleration right here is a lot faster than the acceleration over here on this flat rack. So because of that, you allow it to pick up speed at a lot faster pace, and that's why it actually goes to the ground faster. So this is pretty like kind of elementary level. This is just how an object rolls from the top to the bottom, but it's actually a pretty important concept when you actually want to design things like rockets or airplanes or other objects like that actually move under the influence of gravity. So lots of applications to this, even if it's a basic concept.
I think we actually basically showed these, so can we do it?
Yeah, absolutely. Yes, so think about it. This is a shortest path, and this is the longer path. But what happens when you actually race these together? Ready? Okay, and see, no contest. The Cartesian coin is clearly the faster method.
Awesome. So that's a little bit about kinematics. We'll talk more about kinematics in a second. But for now, we're going to come over here and talk a little bit about some magnetism and electricity. We have these units over here that we're going to show you guys. And have any of you guys heard about eddy currents before? Or magnetic field lines? So we have a demo that will show you about magnetic field lines, as well as a demo that will show you about eddy currents.
We're good.
Give us one quick second. I'll move over here. Awesome. So I have this tube here, and this is just a conducting tube. And then I have these two magnets, very strong magnets. This one and this one. They are about the same weight. So if we drop them both at the same time, we expect them both to hit the ground at the same time. But what the special thing does here with magnetism and electricity, as you guys might know, is you can drop a magnet in here and something pretty cool will happen. So this might be kind of hard to see in the video, so you want to really pay attention closely. So what I'm going to do is I'm going to drop one of these magnets inside of here, and we're going to see what happens to it. 3, 2, 1. Where'd it go? Oh, there it came out. So it looks like it came out, but you might have noticed that it actually went pretty slowly. So I'm going to do that one more time so you guys can see. Oh. Wow, that took a long time, didn't it? But what if I drop the same magnet here? Well, that's really quickly. It really falls really fast. So what I'm going to do one more time is I'm going to drop both of these at the same time if Alex wants to help me with this. You want to hold this for me? Look at, it's going to be really hard to see, but you want to check to see when both of them reach this bottom point right here. Are they going to reach at the same time or different times? Well, just based off what we saw, we think maybe it'll be a different time. 3, 2, 1. Wow, this one went by super slowly, and that's because of eddy currents, which involve magnetism and electricity. So just one more thing about magnetism, as you might know, magnetic field lines, basically they go around our Earth, as an example. The Earth has its own magnetic field lines, but also when you have a magnet, it creates its own magnetic field lines. So here's an example of a magnet that I put inside of a cube. This cube has little iron filings that inside the water. And I'm going to shake it up. And you're going to be able to see here that these little iron filings make little magnetic field lines. And those are circular. That's because this magnet has a north pole and a south pole. And the magnetic field lines basically wrap around the north to the south.
Kind of like our Earth.
Yeah, just like our Earth. And then there's other cool things that we can do with magnetics as well. We can use magnetics to prevent other sort of forces from happening. So for example, I have a magnet in this little device here, and there's also magnets here. Now if I were to spin this here, it would stop because there's friction, right? There's friction on the surface. If you guys haven't gone over friction yet, friction is basically a force that resists something from moving in a certain direction. And it has to be connected to a surface. Unless you're talking about something like air resistance or drag, or something a little more advanced. But we're going to talk about just surface friction for now. And you may have heard that there's two different types of friction, kinetic and static friction. This one in particular is going to actually have neither. And the reason for that is because these magnets are going to prevent this little spinner device from spinning and producing friction. So as we know that if I spin on a table, it spins, but then it slows down really quickly because of friction. But let's try putting it on this magnet device where there's actually no friction because it's not connected to a surface. If I spin it, you want to see closely, it's not stopping. And that's because there's no friction there. The only thing that's slowing it down is air resistance. So that's a pretty cool demo you can do at home. These devices only cost like $15 to $20 on Amazon if you wanted to get it for yourself. They're really cool, I think, to put on your desk and whatnot. So while we talk on the same topic of magnetism, we're going to show you a few demos in a minute that have to do with electricity. You guys may have learned that magnetism and electricity are very closely related. So we're going to toggle to some slides real quick to show you a little bit of pictures and diagrams about what magnetism and electricity really are. Cool, so here's a little bit of an introduction about what electricity and magnetism is. I'm sure some of you guys have already heard about this before or learned about it a little bit more in detail. So electricity we know most commonly and a long time ago, Benjamin Franklin, a lot of people say that he discovered electricity by holding up a kite with a key on it and then getting zapped by a lightning bolt. So here's an example of a natural force of electricity, which is the lightning bolt through the sky to the ground. There's a little picture of Benjamin Franklin as he quote unquote discovers electricity. And electricity is performed through two major parts of an atom, an electron and a proton. And what the electron is it's a little particle that moves around an atom. An electron, there can be more than one for an atom. In this picture, this is just one electron and one proton. And basically, the flow of electrons is what produces electricity. And most commonly, electricity is applied a lot in the real world through circuits. So you can see that one example is the circuit board on the right. That might be part of your computer. And another version is these cars on the left. You use electricity to jump your car if its battery is dead by using the electricity out of another car. We also know that many common circuits involve light bulbs. And like I said before, electricity occurs due to moving electrons. So let's show you a little bit about some electricity demos that we have. Cool, so first I'm going to show you this device. What it is there are two balls here with some capacitors, and this little device that you turn basically uses static electricity and stores it into two giant capacitors. If you guys don't know what a capacitor is, it's basically just a device that's able to store energy if you pass electricity through it. So what I'm going to do is I'm going to charge it up by turning this. And then Alex over here is going to help me out. You might want to get the camera a little bit closer just so you can see it.
Yeah, so right now these two balls right here are building up a whole bunch of electric charge. But the charge is opposite. This right here might have negative charge, this right here might have positive charge. So what happens when you get negatively charged object next to a positively charged object? The electrons want to jump from one surface to another, but they're too far away. So how can we fix this? What if we move them closer together? There you go. A giant arc went through the air as soon as they were close enough to overcome the resistance that air gives. And air gives a lot of resistance. But if you move it really close, it can generate sparks like this.
Yeah, that's the same way that in general lightning works in thunderstorms that you see from static electricity. And the clouds and your ground collects, in the area between it collects a lot of charge, and there needs to be a discharge. Sort of like how between these two capacitors are sort of like the clouds and the ground.
Yeah. And what actually is in this arc right here, that's just a giant flow of electrons. We're seeing the electrons interact with the air, which flows. So that's why we see lightning.
Let's see what else we can do with electricity. We have this guy over here. This is called a Jacob's ladder. And like how Alex was talking about, electrons like to go from things that are positive or negative. And depending on how you do your circuit calculations, it's pretty common to consider electrons flowing from positive to negative, but actually in reality they go from the negative terminal to the positive terminal because electrons have negative charges, and negative charges really want to connect to positive things. So here's an example. There's two terminals in the Jacob's ladder. One of them is going to be charged very negatively with a lot of electrons, and the other one is going to be our ground, which we're going to say is the positive terminal. So if I have this hooked up to an outlet, and what I'm going to do is I'm going to turn it on, and I'm going to see what happens when you put a lot of negative charge on this negative terminal. So you can see, this might be a little hard because of the light, but if I stand in front of it, we have this casing around it because just like the last demonstration we showed you, there's a charge that's building up, and when there's a lot of electrons on one side, they really want to get to the other, so they bridge the gap and jump to the other side, producing this stream of plasma through the air.
So why does the actual arc go up?
Great question, Alex. So first off, you can see that I have it a little bit close towards the bottom. That's just basically to start that arc because if you've ever heard of resistance before, resistance is basically something that prevents the flow of electrons. And air really does have a resistance. So if I get these two terminals close at the bottom, I can make the resistance as small as possible because there's the smallest distance between the two terminals. But then as long as it gets a really strong connection, it's able to flow up all the way to the top. Did you want to add anything to that?
Yeah, so the arc is actually very hot because as the arc travels through the air, it heats up the surrounding molecules. Now, what do we know about hot air? Hot air rises. So when it gets hot, then the actual air pushes it up to the top until it gets too far apart and the arc breaks. We have another electricity demo over here. You pan over to the left.
Yeah, so this guy is called a Van de Graaff generator. And basically what it does is there's this belt here, and the belt goes up and down through a motor, and it creates static electricity off this belt at the very top. So you can see it's going pretty fast right now. We're going to slow that guy down a little bit. So what's going to happen over time is it's going to be building up a lot of static electricity. And just like the last demo we showed you, when you build up a lot of electrons, they really want to separate from one another because if you have a lot of negative charges, they really want to be connected to the positive charges. So you can see here that we have these foil things here, and if you're able to build up enough static electricity, they will start pushing them off because they'll be charged with a lot of electrons. But as I'm touching this guy, it's shocking me. That's because I am standing on what we call a relative ground. And a relative ground is something that's pretty neutral, whereas this guy is pretty negatively charged. So every time I touch it, it's shocking me, and its electrons are going through my body connecting to the ground. And we have this plastic casing here. Plastic is generally considered an insulator. So that's one of the reasons why the electricity from this bell are not going straight to the ground. Instead, I'm a better conductor than the plastic. And why do you think that is the case? Why am I a better conductor than this plastic thing that's connected directly to the ground?
You have a lot of stuff in you.
Yeah, what kind of stuff do I have?
A lot of watery stuff.
Yeah, so water is actually a really good conductor, which is one of the reasons why if you're in a thunderstorm, you don't want to be inside of a pool. So as I'm touching this guy, there's going to be a lot of discharge from this bell. And there's a lot of cool things you can do with Van de Graaff generators. This one's a little bit older, but newer versions collect a lot more electricity. And if you're able to set it up correctly, you can get a lot of things to actually fly off. So yeah, that in general, that sums up most of our demos revolving around magnetism and electricity, but we'll show you a few more that are related in the future.
What if I put my hands on here? Well, then all the electrons are going into me and possibly into my hair, which makes it stand up. It's not really doing it right now, but you can kind of see it.
It looks like they're slipping up a little bit, Alex.
A little bit. I could just be my hair. Alright. Well, that's a success rate of like 50%.
Yeah. This guy's a little bit old. Plan on getting a new one soon. So we're really excited if you guys want to come check out our other videos or come in person hopefully in the future. We can show you guys a really cool one that we're planning on getting. So that sums it up, like I said, for electricity and magnetism. Now we're going to move over here to gravity.
Hey everybody, so it's me again, and today we're going to be talking about gravity. So a lot of you might have heard of gravity as being this force that kind of attracts two very heavy objects. For example, the Earth and myself, or the Earth and anything like these weights. And the heavier the weight here, the stronger the force. But what fundamentally causes gravity? Well, that's still a bit of a mystery. We're still discovering new things about gravity every year. Now, originally, you might have heard Sir Isaac Newton sitting under the apple tree with the apple that fell on his head, which made him wonder, well, what actually made the apple fall on my head? And so back in his time, they just thought of gravity as this attractive force between two very heavy objects, or even light objects. Like myself, I have gravitational force attracted on other things. But they didn't really know what physically caused that. Now, 300 years or so later, this guy named Albert Einstein comes along and says, no, so gravity is actually basically something that happens when you curve space-time. So what do I mean by that? Well, look over here. This is a table that's very stretchy. We use this all the time. You've probably seen demonstrations like this before. But what it means is that basically this is our universe. Our universe has, you can think of it like fabric. When you have a very heavy object, a very massive object like this, it actually distorts the universe around it very slightly. But this distortion is a lot higher when you have very massive objects like the Earth or the Sun or a black hole. So what does it look like? Well, this is our Earth. This is our universe with no gravity or anything. And then this is a very massive object. Nice. So as you can see, this massive object distorts the space-time around it, but it distorts it very much immediately around it, which is why when I'm very close to the Earth, the force is very strong. But look far away from the Earth, the force isn't as strong. And this actually drops by the inverse square law. It means that if I double the distance, then the gravitational force goes down by a factor of 4. So, what does a solar system look like? Well, a solar system is when we have a very massive object like a star or a sun at the very middle. Now, this dents space-time a lot. Now, when solar systems are forming, there's not just the sun. There's a sun and a whole bunch of other stuff. There's rocks, there's ice, there's gas, debris. Now, what does this do? Well, it starts to orbit the sun. So let's go ahead and make a solar system. Now, as you can see, when you have objects very far away, they orbit very slowly. But when you have objects close, they have to orbit very fast. And this is because if the force is a lot stronger toward the star, then if you get a lot farther away, you don't have to go as fast. And if you get really close, you have to go a lot faster. It actually accelerates you faster, or else you fall into the sun. So the good thing about this is these actually don't fall So objects don't really orbit the sun in perfect circles. Now, it might seem like they do because if you look at pictures of planets and asteroids, they're perfect circles around the sun. But instead, these are what are called ellipses. So let's say I have this comet right here, and it goes very fast when it's near the sun, but it goes slower when it's far away. This is actually how comets work. Usually comets spend their time, maybe down over by Pluto, but then they'll come closer to Mercury, or to the sun, and they'll have to go a lot faster, basically to avoid being sucked into the sun. And that's one way to think about it. Now, there's other things that you can do with this, which is, for example, what happens if gravity is too strong? So, can you actually break things apart with gravity? And the answer is yes. So, you might notice that, let's say I have this moon right here. Now, a moon basically, as with anything in the solar system, is just a bunch of rocks basically held together by the gravity. So we're gonna show that with these three heavy balls, and we're gonna show what happens when they orbit the planet. Now, when they're far away from the planet, they stick together because of their own gravity. But when they get too close to the planet, look what happens. They get torn apart. Now, why is that? Well, that's because when you have a very big object, and you have a distance between, say, I'll show you. If you have this moon right here, the difference in gravity in on this end versus this end is not that much. But when you get really close to the planet, there's a big difference in gravity between the closer side of the planet and the farther side away. Now the side that's closest to the planet wants to spin faster because you're closer to the planet, you have to spin faster. But the parts farther away from the planet want to revolve slower. So it turns out if this difference is big enough, and this is called the Roche limit, when the moon gets too close to the planet and it's torn apart, you don't have a moon anymore. Instead, you have rings. And this is actually how Saturn got its rings. It's been theorized that in the past, Saturn's rings were actually moons. But they got too close to the planet and were torn apart by the gravity. And eventually, one day, they might coalesce into moons again, and then get torn apart. It's a pretty constant cycle. So, one thing you can use is...
We can walk through? Okay, cool. Yes. Thank you.
So another thing we can demonstrate is why does everything in the solar system spin the same way? Because, I don't know if you guys have ever noticed, but yeah, whenever so all the planets in the solar system will all spin the same way. Now they might rotate opposite directions, such as Venus, but everything in the solar system goes the same way. You don't really have any stragglers that go the opposite direction. And let me show you why. So let's say we have everything spinning in this direction. Now, let's say we have one lone survivor right here in the opposite direction. Over time, they either get knocked or something that basically changes their direction. Eventually, you have a system where there's a net balance of spinning objects in your solar system, and none of them go the opposite way. So, and would you like to add anything about gravity? So, yeah, I think that's everything that we have for today, for gravity at least.
Yeah, we're going to toggle to some slides to show you some more pictures about gravity. So here you can see we have two images about gravity. One of them is the bigger one on the right. That's an example of two stellar objects and their gravitational fields between both of them. And then the very bottom left one is a picture of the Earth. And the Earth has its own gravitational field, as you probably know. It's different on different planets. And another thing that's super related to gravity is if you guys have ever heard of space-time. Space-time is a really modern way of researching physics and gravity in general, and it involves a lot of high-level topics that you can learn if you want to study physics in the collegiate level, involving things like general relativity and special relativity. And gravity gets really complicated. There's actually a lot of things we don't know about gravity currently, and there's a lot of research going on. For example, if you've ever heard of LIGO, LIGO is one of the brand new, or at least recent, research projects that's involved a lot of collaborators internationally that's helped us discover what gravity really is. And what it actually did was it helped us find or detect the very first gravitational waves. Gravity is a really weak force, as Alex was mentioning, in comparison to other things. So yeah, now we're gonna go to our VP of Communications, Ashley, and she's gonna show you some demos about thermal physics.
Alright. Hello. So yeah, I've got a fun little setup here. I think what we're going to start with is by looking at how heat causes things to expand. So basically what happens is heat is just the way that we measure the energy of things on like a molecular level. So when we take like say this metal ball, it has like a certain set size, it's pretty cold to the touch, and it's not like very energetic, it's held together pretty strongly by those interlocal bonds. So what we're going to do is I'm going to hold it over this hot plate here. And you can see at this size, it fits through this little metal hoop. But we're going to set it here for a little while. And while we're waiting for this to heat up, I can kind of show you the process of what's happening with this fun little hand boiler here. So with this hand boiler, we have a liquid that's being held inside of this like glass tube. And then there's also like a set amount of air inside of it. So when I hold it in my hand, the heat from my hand is going to heat up the air inside of there, and it's going to force the liquid to go up the tube because of how that air is expanding. So you can kind of see, now it's like bubbling up in there, and that's how a hand boiler works. So that's super fun. And then you can do the same process to let it go back down. But I think I'm smelling some hot metal here. So let's see if it still fits through our little hoop. Oh, it does.
If you freeze the heat in the ice one.
We're just gonna,
We're gonna accelerate the
we're
process.
gonna get as
here.
much heat as we can. Don't do this at home. This is extreme temperature stuff. Our blowtorch is missing.
Oh no.
Yes, Joey, be a physics major, you play with blowtorches. There's a hot plate.
We have 6 of these.
Yeah, so while we're waiting for that to heat up, if you guys have any questions about any of the demos that we've done so far, feel free to pop it in the chat. We'd be super happy to answer any questions that you guys have.
Let's attempt
Alright,
extreme physics.
here we go. Still fit?
Oh,
there
it
we have a
does.
little bit of resistance.
Okay.
Blowtorch missing.
Yeah, well. You can hear the water sizzling on there. So let's see, let's try to do another thermal demonstration while we wait for this to heat up. So I've got this can full of absolutely nothing here, full of air. I'm gonna just dunk it in the water real quick so that we have some measurement of like when it's gonna be heating up. And then set this
Probably want a
on.
little bit of water. Yeah, so it turns into steam.
Yeah. So you can see some of the steam coming off that there. Basically what we're wanting to happen is we want the air and whatever water is left in there to heat up and expand. So I'm gonna wait to see some steam coming off that. And then once we see the steam coming off and we know that the air inside is hot and expanded, we can take the can and flip it upside down into the cold water.
And what's gonna happen when it does that? It's just gonna be a regular can, right, when you pull it out?
So you
Nothing's
think,
gonna happen.
yeah, so not to spoil it, but we're hoping that this hot air, when we flip it over into the cold water, will get trapped inside of the can and it'll rapidly contract. And that difference in pressure. Okay, you ready? We're hoping this will make the can collapse.
I'm surprised there's so many viewers, honestly.
go first attempt. Hey. So I didn't apply any pressure there. And the can, you can see that the sides have collapsed a bit.
That's a real can crusher for you.
Yeah. Oh my gosh, we're going in.
Do not try this out.
Yeah, it's very irresponsible.
Ooh, that is getting hot.
The rest of
and
the taste
sharp.
in it, yeah. We're really expanding this metal.
We're doing our best here.
All right. Ready?
Okay.
Yeah.
It works!
This does not fit through. Oh, there we go.
It looks
The
very
It cooled down.
But yeah, you can see that.
Alright, who wants to clean that off?
All right, so that is
Is that
it
still hot?
for thermal physics. Yes, this is still hot.
Put it in the water. Oh, did you already?
Cool.
Yeah, it's not
So
like,
now we're gonna move
Okay,
over
then what it
to something else with our president, Josh Lewis.
Hello, everyone, and welcome to the other half of our space adventure. Today, we are going to be talking about vacuums. That thing that you hear every now and then in your parents' house and exists out there in space. So vacuums are pretty interesting, and what they actually are is just an absence of stuff. When we don't have some stuff there, an interesting thing happens. So in here, we have just, normal pressure, nothing strange here. But when I put on the vacuum pump, which puts a vacuum in here, we're going to see something interesting. We can see the balloon is getting bigger. It's getting a lot bigger until it takes up the entire space there. And then I turn it off. I disconnect this, like so. And now, we've created a vacuum and we can just move around. And what's really interesting is that this balloon that had that original pressure in it of air is now so much more, has a much higher pressure than the outside that it expands. So now, watch what happens when I let the air back in. It shrinks again back to its normal size. And now, it's just a balloon. So now I will show you this. This is another interesting device in that it creates a vacuum. So, if I just put it on this table, this nice flat table, and I try picking it up, you can see that it actually requires a little bit of force to pick it up, right? And that's because it's actually creating a vacuum right here as I pull it open. So if I show that again.
Tell him to zoom out a
You
little.
can see that?
Zooming.
So the air in the normal atmosphere is pushing down on this, trying to keep it still. And then when there's not as much air in there to push it out, it becomes more difficult for you to lift it up.
Are you gonna answer the questions?
So now, let's go over to my favorite demo that we have here.
question right
Someone asked in chat what my favorite demo was, and this happens to be it. You may have heard the old adage that you cannot scream in space. Turns out that's true.
Well, you can scream.
You can do your best. This is me screaming. We put that in there, and you can hear it still. But what happens if I remove the air? What happens if I remove the stuff that allows the sound to travel? As we come down to about a 20th of the percent of atmosphere. We're getting close. Let's say that does it. So now, the only sound you can actually hear is just the vibrations that are coming out through this bottom bit here, okay? But if I let the air back in, you'll start to hear the actual ringing again. So I'll just bring this closer. Just pay attention very closely to what this sounds like now versus now. The ringing comes back. All of that sound that's actually in there, it travels through the air that's around it. And so if we don't have any air or stuff for this sound to travel through, then we just don't have sound, which is an alien experience indeed. We'll now show two more things with these fun little vacuums. I will show off some interesting little treat here, a marshmallow. And you can imagine this marshmallow is kind of like a sponge, right? You can't really see the holes, but there are tons of tiny little holes in there stored with air. So we imagine, well, what will happen if I try to get that air out? Will it just come out and it'll shrink? Or will it act like the balloon and start inflating up? Well, the answer is a little interesting. First, it starts to increase, as you can see here. It's about, if you want to get closer, it's huge. And then it starts to decrease in size because that air is actually escaping. Unlike the balloon, the air can eventually get out. So now, it's a little bit wrinkled and the air has kind of escaped a little bit. I'll give it just one more moment. And then, I'll disconnect it. And then, we will let the air back in, we'll see what happens. So now, when this marshmallow doesn't have any air in it, this is what it looks like. This wrinkled husk of a poor marshmallow that we did this to. This poor marshmallow will live in our hearts. No air. And now, we'll show this fun one. I like this one a lot. So you can see here, just two things that kind of fit to each other. I can pull them apart pretty easily. But I can pull a vacuum on the inside, and that's when something interesting happens. So, let's hope that this is the correct one. I do not like this adapter. So we're going to do this one instead. It has an
He keeps
ear back.
zooming in, and it's blurry.
Go ahead and turn it on. There we go.
Yeah, just like the optimal zoom.
So just every time it zooms, it doesn't focus. Okay.
So then disconnect it. So now I have stored in here a mobile vacuum. I can move this vacuum wherever I want, over here or over there, and it's still a vacuum. And it's very hard to pull apart because there's not that much air in here to push outward. So the air on the outside in our normal atmosphere is pushing inward on this and keeping it still. Now, Alex, if you grab the other half, we can see exactly how much force we put on this until it opens. And that one opens pretty easily after you put a good amount of force in.
It's my muscles.
Yeah, Alex is too strong for this one, unfortunately. We will use this one. We just have to be a little bit more creative. Give me one moment. I really dislike this adapter, so this is the best way to get on it.
In engineering school, this is actually pretty common.
Yeah.
Not having things work.
Not having things work and having to try something a little silly to make it work. All right, Alex, if I can get a little assistance.
Yes.
If you could just turn that thing on, so I can get this balloon wrapped around. And turn it on, so I can try that again. Just like that, there. And this to be in there. unfortunately not going to work on that one. So I'll have to really want it. Open it up. We saw this one earlier. It just has a little bit of a poor adapter, making this a little bit more difficult. But it should be on it now. Let me just hit the printer. Go down just a little bit more. We close it up. We disconnect it. And now, this one I think is one that holds a little bit better. Well, looks like it held pretty well because, you know what, it broke. So we're going to try that again. All right, Alex, just give it a good. Okay, so this one actually works. So you can see that I put all of my body weight on it, and so did Alex. But now, I can open it very easily by just letting the pressure back in. And then, voila, it opens. And that is the end of our vacuum demo. This is definitely my favorite section.
While we're still on the topic of vacuums and air pressure, we're going to move over to Paul, who's going to do a demo for us.
Hello. So in this demo, we're going to take one of these air cannons, which you may have seen before. What it does is when you pull it back, it actually launches air. So if you were in person, you could kind of see or feel, actually just feel what it feels like to have air come out. But to kind of visualize what the air is actually going to be doing once we launch it from this air cannon, we have a smoke machine down here, which if I turn it on and then take some of that in, we can see a slight puff of air. I think I have a little bit.
Put the end of the nozzle onto there,
And then pull it.
and pull it back a little bit, not too hard. Just a little bit. That way so we can see it. Yeah. Close the doors.
Whoa.
There we go.
Physics. Oh, you can see the ring.
You can see a little bit of a ring. It's kind of hard to get it perfect. But with this smoke, we can kind of see a little bit more of what the air will do when we launch it. And now we're going to try the same thing with a slightly bigger one. Here.
We've got a lot in this guy, so make sure you're paying attention. This is a really big air cannon. Ready? 3, 2, 1. So you can see that vortex as it goes through the air. Might be a little bit hard to see on camera, but really cool to see in person. So if you guys want to come join us next year, we'd be happy to show you a lot of these demos as well in person, and you guys get to play with them. So now we're going to move over to this section over here. That sort of wraps up our talk about vacuums. Just a few little things to point out. Here's a few little demos about kinematics, mechanics, and whatnot. So first I have this hot water. So I'm going to pour into this mug. And then we're going to put this guy on top of it and wait for a little bit. This guy's called a Stirling engine. This one's powered by steam. So we're going to give that a good minute or 2 minutes to warm up and settle while I talk about some of these other demos. So this one I'm sure you've probably heard about before. It's Newton's cradle. This one involves a topic that you might have heard about before called conservation of momentum. So I can pull this ball out and then let go, and you can see that the momentum is transferred between the balls and goes back and forth, back and forth. So these ones in the middle are generally staying pretty stable. It's conservation of momentum. But a cool thing is we can also pull back 2 of these. So we have the momentum of 2 of them being swung, and then it moves 2 of them back. See that? 2, 2, 2, 2, 2, and the one in the middle sort of stays in the same spot. And then even do the same thing with 3. Oops. Even do the same one with 3. Pull these guys back. It's a little bit wobbly, but you can see that there's 3 of those guys moving back and forth. Let me fix this guy real quick.
Yeah, I'll do that again for you. So if I do a little bit more stable this time. There we go. So the center one moves like there's it's basically just swinging freely. But basically what's happening is all the momentum that's in these 3 balls is traveling to this side. But there's only 2 balls, so one of these is free to keep going.
Cool. So that's conservation of linear momentum. Another type of momentum we have is angular momentum. So I have this guy here. It's called an Euler's disk. You guys might have heard of Euler from some other concepts. So what I'm going to do is I'm going to take this Euler's disk, and then spin it, and we're going to see what happens.
Euler's the guy who basically just made all of our math.
Yes, you can see it's spinning pretty normal. But as it gets lower, it looks like it's actually starting to speed up and starting to make a louder sound. They said that has to do with angular momentum, but how is that working? What do you guys think? This guy's pretty low friction, so it's going to take quite a while for it to actually stop. I'm going to give it one more try just to show you guys with a little faster speed. That wasn't quite fast enough.
There you go. That's a good one.
So it's going decently fast. Starting to wobble now. And then we'll see it's going to start to speed up. So if you think about it, originally we had this Euler's disk that was spinning this way, which means it had a really large axis of rotation and a really big surface that it had to spin completely. But when it's at this angle, spinning this way, the area that's rotating is really this outer perimeter, and this outer perimeter has significantly less area than the top and bottom sides. We won't get too far into the math involved, but generally for angular momentum, you have something called a moment of inertia. And this moment of inertia, the way that it's rotating right now, is significantly less than the moment of inertia when it's completely standing up and spinning. So we'll let that keep spinning while we talk about some of these other things. I have the Stirling engine now that we were setting up before. And let's see what happens now. I'm going to spin it. I think probably the other direction. There we go.
Yeah, oh.
So what the Stirling engine, what it does is there's this hot water underneath here. And there's basically this pressure plate of foam that goes up and down. And the Stirling engine basically uses temperature differentials as well as this little vacuum space inside that allows it to continue going. So as the water starts to cool off, it starts to not like power as well. But when the water is hot originally, there's a lot of steam, and when we keep going for a super long time. So you can see this guy's still going. It's not going as fast as before, probably because my water is actually not too warm. So, yeah, it'll keep going for a pretty long time. Because there's also a lot of frictionless estimated surfaces on here through the joints of one another. Let's go here, talk about some more vacuum stuff. Sorry, I said there was only those demos over there, but we actually have one more right here. This is, guess what this is? What does it look like to you guys?
Trash is not the right answer.
Well, if you guessed a leaf blower, you are correct. Because this guy is just a general leaf blower that we duct tape to a plank. So what it's doing is it's blowing air up. You can see it's blowing kind of a lot of air. We have it angled in such a way that ideally it's pointing straight up, but as you can see, it's slightly slanted. So what I'm going to do is put a ping pong ball right here. And wow, you guys see that it's floating. You guys know why that's the case? It's pushing air up, so why wouldn't it just like push it off to the side or to the other side? Well, actually what's happening is this vortex of air, like we said, it's going up, it's pushing air out of the way, so it makes space for other air from the sides to come in. So in general, what's happening here is, yes, the air from the leaf blower is pushing it up, but what's holding it in the center is actually the air around it that's encapsulating towards together.
You can't see all
So I can do
face.
cool things like even turn this at angles, and you can see that it still goes. Because that air from the side is rushing in, holding the ping pong ball together. You can actually go pretty far. It's pretty cool, this leaf blower to play with.
How far can you go?
Well, let's see. What? Oh. So at some point, the force from this air pushing it up is not strong enough to counteract the gravity of the ping pong ball. If you do some geometry, you can do some of those calculations, but we won't show you guys those today. So yeah, you can just think of this like making a Newton's second law. Most of you guys might know about called an FBD, free body diagram. So if you were to define the forces on here, you'd have a force from the leaf blower pointing up, you'd have the gravitational force pointing down, and then also the force from the air cap going in. So it's really like a three-dimensional FBD because you have air rushing in from every side. If you go more into talking about dynamics, or if you're interested in learning more about like air resistance and drag, consider taking a physics course, either at high school level or college. You can learn more about this kind of stuff. Super relevant to airplanes and helicopters and lots of cool aerospace related things. So yeah, and as you guys can see here, our Stirling engine is still moving, which is really awesome. Just powered by steam. So yeah, that's all of the vacuum demo stuff. Did we want to go over these?
Yeah, those are fun.
So we have these cups, which are basically just these beads. Get this ping pong ball out. It's angry. And basically these are just strings of beads that are connected in a really long length and then coiled up in this cup. And assuming that it's not tangled, we can show some pretty cool phenomena with this. So what I'm going to have Alex do is he's going to hold up this cup really high. And then he's going to toss one of the ends out, and we're going to observe what happens to this section. So pay attention mostly to the height of the beads as it comes out. Okay. Ready? Wow. So first off, you can see even by pulling a few beads out of the cup, a lot of it is able to come out. And that's really due to momentum in general, as well as gravity pulling down those beads that are in front of it. You can think of it sort of like a siphon, but in this case it has to do with these beads. I have another larger one right here that we're going to show you guys, in case you weren't able to see about the height thing that I was talking about. So we're going to do them one more time, and then we're going to ask you, what is exactly happening right here? So make sure you're observing that, and then also explain why do you think maybe that's happening.
Probably go to a higher
Yeah.
surface. We have this bench right here.
So pay attention to the cup in general.
Ready?
A little bit tangled. Oh. Well, you might have seen it for a split second, but the beads were really coming out of the cup at a pretty high distance, like several inches. It was really pulling those beads up. So the faster it goes, the more beads that come out of the cup. You'll see that more of them come out of the cup at a higher height, because the force as these beads come down, starting from the beginning, when you have that length of beads that hits the ground, really increases because there's a larger length of beads, so there's a larger weight force, what we call a weight force that's pulling it down. And if you wanted to do a FBD or free body diagram like we talked about before, you want to make sure that all of your forces cancel out, or that if you have Newton's third law, if you guys have heard about that, for every action there's an equal opposite reaction. As you have beads coming out of the cup and being pulled down by gravity, you need another force that's able to pull the beads up out of the cup. Otherwise, your cup would just go down, or you'd have your beads snap together. So that's really Newton's third law of forces.
And also the coolest part about this, in my opinion, is usually we think of physics as something that's been done a long time ago. Everything in physics is, perfectly cemented. We already know everything. But in fact, this right here was only discovered 10 years ago or so. We're actually still learning about, specifically why it is that how the forces work to get this chain like kind of hovering above the cup, and specifically how can we increase that length and how does the angle actually affect it. So yeah, this is still actually being kind of looked into. You're not 100% sure why this behaves the way that it does. So that's the cool thing about physics. You're always discovering new things each year. So I'm going to go over here and we're going to have some more demos, specifically in friction.
Alright. Hey people, so we've got this really cool setup here. We have some ropes attached to a couple of phone books, which are being pulled aloft. So an interesting way to think about this is if we were to make a free body diagram of this system. So we have gravity is pulling down on our swing, and then we have these ropes that are pulling upward and to either side of the tension force. And we know that since it's not accelerating and it's barely moving, that there's no net force happening here. So we've got the downward gravity and then upward tension, and then we have tension to the right and left. But you'd think that the tension to the right and left would actually pull apart the phone books, but it doesn't because of friction. So from our perspective, the pages feel really smooth, but if you were to look at these pages on a really small level, really up close, then you could actually see the roughness in the page. And there are ridges in the pages. And so when you have two pages that are on top of each other, they're going to interact with that friction and create a small force that will resist movement. So basically, when we have all of these stacked on top of each other, the sum of that force is enough to keep it from pulling apart with either the downward force of gravity or force of tension. And you can even support a whole person on it and it won't fall apart because of friction. So yeah, that's that one.
So are you saying that there's no tape or anything holding these two phone books in the middle together?
Yeah, it's just the friction of the bridges. And then we've just got some bolts through this just to connect it to the swing. But yeah, that's all friction.
There's tape on the outside, that's just
Right.
Yeah, I don't know if you mentioned this, but I actually saw a Mythbusters episode where they actually held two phone books together, and they actually couldn't even get two tanks to rip it apart. Super strong friction force, depending on how you use it. It's really awesome. Thanks for showing us that.
Then we've got one more over here.
Alright, so this is our very last demo that we're going to do, and we did save this for last. So this is for talking about sound. Now, as you know, sound is basically made up of compression waves going through the air. Now, the human ear can hear about 20 hertz all the way up to about 20,000 hertz. And basically what that means is if I basically have a pointed space and the waves flow through it, 20 revolutions will pass every second. So this is basically just, so when I have something like 49 hertz, that means that we have 49 waves coming through every second.
Or should we do
So
the
what
panel?
does it actually, how can we actually visualize
We
this?
could do it just
So
like right
let's
here.
say that you get
Or
one
we
of
could
those
do it
over.
like
And we've actually put the speaker right here. That it's very basic.
Is that
It's a big
classroom open?
speaker, and we have the substance in here called oobleck. And this is called a non-Newtonian substance, which means if you say it's basically a liquid. It's very watery, but if you impact it, it acts like a solid. So let's say that we have something like a sound wave coming through, impacting it and turning it into solid. Well, we can actually get it to do some pretty cool things. I'll show you. So let's start with a frequency. And actually get it to be mounted. lower frequency, we start to notice different phenomena.
So it looks to me, Alex, like when you change the frequency, it also changes the amount of bumps that are in. And like, why is that?
So that's because the waves that go across this are called standing waves. If you have a very high frequency, then you're going to have a lot of little bumps. But if you have a very low frequency, you're going to have few bumps, but they're going to be a lot bigger. Versus high frequency, it's a lot more smooth. But then I lower the frequency, and you start to get these waves in there. And look at this. So you can actually get things where it looks like the goo is like trying to escape. Now what that is basically every time we get this pulse through here, it solidifies it. But then it wants to,
Yeah, I think that's
but then
the
once it goes down, it turns into liquid again. And it's solid and liquid. And it's basically this cycle
Still
that
focusing
makes it
on that
act
side.
kind of in this weird, like almost living way. Look at that guy right there. So we found that usually 50 hertz is usually something where you get what's called resonance, which means that every single time you give it a pulse, it constructs upon itself. It builds like bigger things here. Versus if I were to go to just a really high frequency, and basically everything cancels out. Down to a low frequency, not too low, otherwise it doesn't really do anything. But 50 to 60 hertz, you get some pretty cool stuff.
So I imagine there's a lot of really cool things you can do with this, Alex. Like, what if I were to play a song that had a particular frequency beat? Could I get it to do the same thing and make it bounce up and down to the music?
You could, potentially, but you don't really notice it a lot in real life just because music has a whole bunch of different frequencies. And like I was saying before, we need kind of a resonant frequency to do this.
Gotcha.
So you get the best results when you have just one frequency, when you can kind of vary it up and down, and specifically hone in on stuff like this, where you get the perfect amount of illusion. And I don't have this on.
Awesome. Thank you so much, Alex.
All right, well, that concludes all of our demos for today. We're going to be doing a 5-minute or so intermission, and then we'll be back to answer any of your burning questions about college, physics, or just life after high school in general. We are going to be doing a panel discussion, and yeah, we hope to see you soon. As a reminder, we are SPS, the Society of Physics Students, and we will see you soon during our intermission. Setup right now. our panel here is going to be why physics? What made you choose this field?
What made me chose this field? Yes, well, for me, physics is kind of like a description of the universe. Mathematics may be the description of, you know, the grammar of the universe, but physics is how it actually happens. You know, we can say everything that's happening in the world can all be described by physical laws and just by physics. And to me, that's really deeply understanding what is happening in the world is physics.
Yeah, I'll connect with that next. So I chose physics because I really liked how broad the field is. You can really do like whatever you want with physics because it's just like Josh was saying, you're just describing the universe and working with the science surrounding that. So yeah, at this school we do a lot of like engineering physics and applied physics, but you can also do like theoretical physics and focus on more like abstract concepts. So yeah, there's just really so much that you can do with it.
I also really enjoy physics because of the many different opportunities there are for different fields you can go into. So a lot of people think that if you're studying physics, you basically can either go on to become like a PhD university professor or like a high school teacher. And while those are two things that a lot of people find a lot of value in, there are a lot of different fields that you can go into with a physics degree, such as in like aerospace, working with lasers, medical physics. There are just so many different things that you can do with a physics degree, and things that are very, very interesting. One of the things that physics that I'm particularly interested in is quantum computing. It's something that is happening a lot at Mines, and a physics degree will help me prepare to work in this field and go on to work with some really big players in that industry, such as IBM, Google.
I just think this part's probably less
It's
interesting.
very interesting the kind of things that you can do with a physics degree.
Thank you. And as a reminder, before we go on to our next question, you guys can probably
We did have 11
type
hours
in the
like
chat, and we will go ahead and ask them to our panel here. So the next question is, how is college physics different than high school physics?
I can answer that first. So the biggest thing that's interesting about college physics is that in high school, a lot of the stuff that you're studying is things that have existed for hundreds or around hundreds of years. So the things that you're studying in high school, like the way gravity works, or the way electromagnetism works, those are both things that people have kind of pretty well understood them in a rough sense for a long time. Once you get to be doing like physics in college, either doing research or in like advanced classes such as a class on general relativity, you'll be studying things that oftentimes have only been really studied in the past couple years. Like I'm in a class right now where we have studied some theories that have only actually been proposed in the last 10 years. So that's really fascinating that in college, the physics that you're studying is much, much more.
Yeah, I'd say the next point, like how the two different, is that a lot of the times in high school, you're working with half of the problem, and that half of it's already been done for you. And so, you know, you don't have to prove that Newton's second law exists and is real. You just get to work with it. Or sometimes in college physics, you'll work with what if gravity was a little bit different? Or what if electromagnetism was a little bit different? You start going into these more general, deeper understandings of physics. And that's what I'd say is what I've noticed the main differences is that deeper understanding and getting to the weirdness of things.
Yeah, for sure. One thing that I said is that sounds kind of intimidating. Most universities will have like courses that bridge that gap between like what you learned in high school and moving on to like the more modern physics. Like we have some introductory general education courses that cover like mechanics and kinematics and then electricity, magnetics, and optics. Before you go into like modern physics and really explore some of the weirder things that physics has to offer.
Well, cool. I actually do want to touch into, a lot of you were mentioning research. What is research like for undergraduate students such as yourself? What do you get to do?
Not every undergrad gets to do it, but if you want to do it, it's something that you can do. It's a path that you can make. For me, I spent way too much time trying to get into research, and the research I'm in right now, I am very fascinated with. It has to do with weird space-times and strange topologies of the universe. It's weird. But I am basically looking at some very strange phenomena that exist in the world and trying to explain it using physics. My actual research, the term for it is fractional physics, or the analysis of fractional systems, or emergent phenomena of fractional systems. I can make the words longer, but it's interesting.
Yeah, so kind of more generally talking about physics, or doing research in physics, the thing is that the things that you're studying in like doing research they're all things that no one has ever done before. So throughout basically all of high school, you're studying things that have been done before and have been proven to be true. When you're doing your own research, you make a hypothesis, you think something is going to be true, but then you have to test it and see if this thing that no one else has ever asked before is actually correct. And I think that's something that's personally super rewarding, to be able to kind of work on something and at the end of it, be able to share the knowledge with the world about how physics is different, or how it can be better understood through your own contribution.
Yeah, and then I don't actually participate in undergraduate research at Mines, but I think that physics has prepared me really well for doing research in a number of fields. Last summer I got to work on research for material stuff, seals, and then this summer I'm going to be looking at some marine biology research at Boulder. So it's really like physics prepares you to like think a certain like scientific way, and then you can really take that and apply it to like a whole range of topics, and it's just super exciting.
So, I know another common question in physics is specifically how important is math in physics? Can you be a good physics major even if you're not particularly excited about the math?
So what I'd like to say about that is there's a very famous Einstein quote that I'm going to butcher, but the idea of it is that you really do not understand physics unless you can explain it to a 4-year-old. If you cannot explain someone physics, what's happening in the world around us, without using math, then you really don't understand it well enough. And that's my opinion, and I think that's the true opinion. That's a correct opinion.
Yeah, so I think that physics and math are really interlinked. But as someone who's like not a hugest fan of math and loves physics, I think it's just like part of that like growth process and getting to explore the universe is just like learning that language that the universe speaks in math. So like even if you don't feel particularly confident, I think that there's still a place in physics for you.
It's almost 12.
The other thing that I'll kind of say is I really enjoyed math in high school, and I was considering doing math as a major, but then I realized that that's kind of like not really as applicable and didn't really have as many things that I could do with it. So the other thing is, while you don't need quite as strong of a math background necessarily, a lot of the stuff you can learn with enough practice. But also physics, if you do enjoy math, you can get some of that by doing specific areas of it. But a lot of areas won't use quite as much math.
Yeah, and we're starting to run out of time, so I'll just do one more question that I have. What is one thing that you wish you knew in high school that you know now? If you go back and explain to your high school self something.
Well, this is more in general about college, not necessarily about physics. But I'll let you know that regardless of whatever you think you're going to be doing in high school, or you think you're going to do in college, be very flexible with what you want. If you could find out that something that you're really passionate about in high school, or something that you really want to do, like you're dead set on becoming a doctor or a civil engineer or something, you might find out that sort of thing is not for you, and you'll just have to change your perspective. So I think a really good idea is to make sure you have an open mind about your future, really find out the things that you enjoy doing, and be willing to change a set path of what you think you want to do.
I think some advice that I wish I would have had going into college is that you need to like constantly be focused on like having a growth mindset and not focus on like how smart am I right now, what do I know right now, and like how does that define my path for the future? Because you're going to be constantly changing, experiencing new things, learning from new people. So if you don't feel like you're smart enough for physics or good enough at math, like there's always room to grow. And yeah, I think that there's a place for, like, if you feel passionate about it, then go for it. You can do it.
Yeah, and I mean, on that note, I spent way too much time in high school judging myself and judging how other people might judge me, to not realize that, you know, people are too busy worrying about judging themselves than they are to judge just me. Everyone is on their own little path to the finish line, and you can't judge yourself based on someone else's path. You get there eventually, and you know, you can't really compare yourself to someone else's circumstances because you really don't know them. So I think, you know, focus inward and on that growth mindset instead of focusing outward on everyone else's growth, because you really don't know what's going on the inside.
Yeah. So yeah, and another one. Tell us about your favorite experience at Mines, whether it's a favorite class, favorite research, or favorite activity.
Well, I can go ahead and get started. So my favorite experience at Mines was I got to take this chemistry class, which was like a molecular engineering course, pretty much. And I just had like the most crazy professor, like off the walls. And he just like made it really fun and conversational. And even though I was in a lecture hall of like 200 students, it really felt like we were all like in it together, having a good time. And even when COVID struck, like he would still come to lectures wearing a plague mask and like really get us all excited about the topic and like relate it back to current events. So it was just a super cool experience.
I think my favorite experiences, they're interesting because they might not be everyone's favorite experience, but mine are the 3 a.m.s I had with friends working on the homeworks together, or working on some terrible project where I had to 3D print a whole thing, but the 3D printer was broken because someone messed with it and broke it, and then I had to fix it. Those 3 a.m.s are very precious to me, just being with my friends and really being in the thick of physics and just life, I guess.
Yeah, kind of building off what Josh said, I think that the culture, at least here at Mines, is that everyone is doing a lot of work. Everyone's kind of struggling through it together, and that really creates an excellent sense of community. So a lot of my favorite times have been hanging out with the friends I've made here, whether that's doing random things, like last night my friend built a really janky electric scooter that basically I thought was going to break every time we rode it, and it was just insane. And that was just one of the things that we have done. There are a lot of these memories that just stuck with me and will continue to stay with me as I think very fondly of.
Awesome. So that wraps it up. Unless any of our panelists have any specific questions or anything else they wanted to answer or talk about, we thank you so much for coming. Anyone else to say?
Thank you for showing up.
Yeah, thanks. And just as a reminder, this is going to be posted later on our YouTube channel. We recorded this as well as doing the live stream. And if you guys have any other questions to ask our panelists, or if you're wondering how some of our demos work, we'd be super happy to answer those. Feel free to reach out to our YouTube account. We have our email that's attached to the YouTube account that you can email. Or I can send you guys some other information on how to contact us. Thank you so much for coming. We hope that this really sparked your interest in physics and STEM in general. And thanks a lot. Have a good one.
Bye again.